very complex or it can be very simple. But the point is, we don't know how it works. The only vision we have is through the data. Okay, and we hope that this data is able to capture the intricate details regarding how the system is observing. So we have an entire grid of information on which we are sampling spaces through this data. And this data gives us some insight into what the underlying system may be. Okay, so maybe if I have to give some kind of understanding, let's imagine that you are in your living room, but your eyes are closed, you're blindfolded. Okay, you cannot see what is happening. So the only access to data, if you want to navigate inside this room, you have access to what you hear. Maybe you can use your hands to touch things, and you can maybe use a stick to know how far things are, how close things are. And what happens is you can use your sensory organs like touch and hearing and maybe even smell to navigate inside your house, inside your living room. What are the equipments and how do you go from point A to point B? Now, as you're navigating, what you're doing internally is, in your mind, you're trying to make a map of how things are. You may imagine that, okay, I know how big my living room is. Maybe I have the sofa placed here, or maybe I have a chair or a table in this part. There is a door, there is a window. So by navigating through your data, you're trying to understand, or you're trying to build a representation of your house, or a representation of that map into your head. Okay. Similarly, within the world of data analytics, machine learning is doing exactly the same thing. Machine learning is trying to look at the data, and from this data, trying to understand how the target system works. Okay, what is the relation between the target system, underlying system, the input data and the output data. And all the different algorithms that we saw are different ways of expressing the same data for the same target system. Now, some of those algorithms are good, some of those algorithms are bad. And how do we know if something is good or something is bad? Okay. So one way of knowing that is we call as a validation of the data or testing of the data. For that, this is the topic for today, where we will be discussing how we evaluate our model. Okay, how do we know out of the several models that we have, which model is good, which model is bad, and how can we navigate through that space? So the first method that we have in front of me is the simplest method that for data science. And the simplest method is, I take my data, I take all of my data, and I divide my data into three parts. Okay, part 1, 2, and 3. The three parts I will call training set, validation set, and testing set. Okay, so let's, maybe a good example of that is, let me imagine my data is 100%. From that 100%, I take maybe 60% for training, 20% for validation, and 20% for testing. Okay, so if I'll take 60% for training, 20% for validation, 20% for testing. And what does this mean? So what this means is, for all of these 100% data points, I know what the actual answer is. Okay, I know the input that goes into I know the input for all of these data points, and I also know the output for all of these data points. But I will only use 60% of the data to train my model. Okay, I will only use this part of the data to train my model. So training my model basically means to learn the parameters of the model. Okay, so for KNN, maybe KNN is not a very good example for this. Let's say for naive Bayes, learning the parameters of the model is learning the probabilities of the target function, and the different features or attributes that we have. For decision tree, this would mean learning the structure, learning the tree structure, that is the entropy, the which node is a decision node, which node is a leaf node, where do I stop, and so on. So learning those things I will do with only 60% of the data. Okay. Once I've done the learning or training with 60% of data, we also know that within our models, we need to choose different hyperparameters. Okay. What are hyperparameters? Hyperparameters are are decisions like uh, how many decision nodes do I have? Okay, what should be the depth of my model? How many what should be my criteria for distance? Do I use Euclidean distance, or do I use Manhattan distance, or things like that? Okay, so how many neighbors do I choose? So decisions like this, for decisions like this, I will use the validation set. Okay, what does that mean? That means I will try different values of these hyperparameters, and I will see how good or bad my model is done on this validation set. So I train with this data, I validate with this data. Why is this validation good? This validation is good because this part of the data my model has not seen. Okay, my training model, the model that I'm trying to fit, has not seen this data. Okay, so let me also reiterate, the main part of machine learning is we are trying to learn the underlying system. For what purpose? Okay, the purpose is that when I come across unseen scenarios for which I do not have the data, okay, when I come across new cases, I want to know for those new cases what should be my prediction. Okay, do I for a new passenger, do I say that that passenger survived or did not survive on the Titanic data set? For a new client, I want to know, do I give this new client a credit card or not? Do I give this guy a loan or not? Okay, so these are the things that I want my model to do. So I want my model to work on unseen scenarios, on a generalized scenario. Now, thus this validation set is trying to simulate that scenario. This 20% of the data the model has not seen, and since the model has not seen this data, I can train the model with the 60% and validate if my training is right or not with this 20%. Okay, and I can do this validation for all the different algorithms that I have. I will do it for KNN, for decision trees, for naive Bayes, for random forest, for logistic regression, and so many other algorithms that I have. I will do this validation for all of those machine learning algorithms. And out of all of those machine learning algorithms, I will shortlist a few of them or shortlist one of them. Once I have that model, okay, I will do some more experimentation with that model. And finally, I will say, I am ready to see if how this model is going to perform. To see how the model is going to perform, I will finally do something called as test set evaluation. Okay. For this test set, for this test set, I have not, my model has not seen this test set. Neither have I seen most of this test set. Okay. So when I'm training for validation set, when I'm choosing hyperparameters, I am like as a data scientist, you are exposed to this validation set a lot. Okay. So there is a good chance that you will adjust those hyperparameters such that your validation score will become better. But with the test set, even you have not seen the test set. Like you've not seen by what I mean by not seen is you are not familiar, or you have not trained the model for the hyperparameter selection for the test set. Okay, so this is a completely new data or unseen data. And on these unseen data, you will again validate your model, you will test your model. And on this testing, you will see how good or how bad your algorithm is doing. Okay, so that will be the test set evaluation. Now, this strategy is a very common strategy or a beginner level strategy that we use for training the machine learning algorithm. What kind of data we can access through this model? So the question I don't really understand. Let me tell you, the model is basically a representation of my system in which I give input and I get an output. The output is the prediction. And we are trying to learn how to predict for unknown scenarios. So the model does not have access to any data, or the model is not providing for us data. What we are doing is we are using the data to learn a model that will represent the system. Okay, and for this case, we will train with the 60%. With the 20%, we'll validate, that is, choose the hyperparameters. And finally, with the next 20%, we will test our model to see how good or how bad we are doing. Now, what are the pros of this system? The advantages or the pros of the system is this is very fast. Okay, since I am evaluating, since I'm not validating multiple times with the same data, my model is very fast. So I'll tell you why I'm telling this when we go to the next case of evaluation, this part will become very clear why I'm saying that this is fast. Okay, it is simple. Of course, it is simple because it is very simple to understand how we are dividing the data and how we are testing it out. Again, the simplicity of this model becomes more clear when we look at the next model. But what are the cons of this model? What is the problems with this model? The problems with this method of evaluation is I have high variance and there is bad use of data. So what do I mean by that? What I mean by that is, let's say that you are training this model for your Titanic dataset, and for the Titanic dataset, you are trying to predict survived or not survived. Okay, and let's say when we divide this model into three parts, we have different distributions of data. Okay, that means here in the training set, I have 70% survived and 30% not survived or died. In the validation set, I have 50% survived and 50% not survived or dead. And in the test set, I have 30% survived and 70% not survived or dead. Okay. So what we see here is I have a different distribution of data for my training set, validation set, and my test set. Okay. And since I have a different distribution of data, uh, let's say for the training set, I am not getting enough representation of the people who have died. I just have 30% of the data for people who have died. That means I have less samples to learn from. If I have less samples to learn from, I think I can learn very well what does it mean for survived, but not very well what does it mean not to survive. So my model will be slightly biased towards people who have survived. If I go to the validation set, I'm validating with a different distribution. Okay. And then if I go to test set, I'm testing with a different distribution. So when I do something like this, I have something called as high variance. Different parts of my model are biased towards different aspects of the data. Thereby, it may not do justice to my data. It may try to learn things that are not of this model. That is problem number one. Problem number two is it is bad use of data. What does that mean? So let's say I have a data analytic problem where I have less data. Okay, so let's say I have already only maybe 1,000 points. Out of those 1,000 points, out of those 1,000 points, I'm using 600 points for training, 200 points for validation, and 200 points for testing. So for most machine learning problems, 600 data points is not too much. It is actually less. Of course, it depends upon the complexity of the problem. If my problem is more complex, I need more data to train. If my problem is less complex, I need less data to train. Generally, we expect more amount of data. And with this strategy, that is dividing my entire data into training, validation, and testing, I am losing this part of the data to train the model. Okay, I cannot use 20% and 20%. So 400 data points I am not using for training the model, which is kind of sad because my model will not be able to learn well. Okay. So to improve over this strategy, we have the next way of evaluation, which is called as cross evaluation or cross validation. Okay, so let me write it down. It's called cross validation. Okay. And let me tell you, the first one is called three-way split validation. Now, data science is a very confusing department because many terminologies is not standard across all people. You will find different people using different terminologies depending upon how they understand, depending upon the domain and so on. But in general, this algorithm is called as a three-way split between training, validation, and testing. This algorithm is called as cross validation. I'll tell you what cross validation is. So let's say I have 100% of my data. What I choose is I divide my data into 5 parts. Okay, 1, 2, 3, 4, 5, and each part has 20% of the data. So let me put it up here. 20%, 20%, 20%, 20%. So we divide our data into 5 different parts, each part representing 20% of the data. Now, what we'll do is we'll do the training of the model in multiple iterations. Okay, we'll take iterations like iteration 1, 2, 3, 4, and 5. For the first iteration of training, what we will do is we will use this, all of these part, the hashed part, 80% of our data for training the model and 20% of our data for validating the model. Okay. Here we are not talking about a test set at this point at least. I take 80% of my data for training and 20% of my data for validation. That happens on iteration 1. On the second iteration, what we do is we take another 20%. So this 20% of the data, in the first iteration, this was part of training. Now this is part of validation. And this training data, first part was fold 1 was part of validation, and now I'm using it for training. In the second scenario also, I'm using 80% of my data for training and 20% for validation. The difference is I have taken a different part for validation and different part for training. Similarly, for iteration 3, I will use fold number 3 for validation and fold 1, 2, 4, and 5 for training. I think you get the point. Okay. So every iteration, we are using a different data or different 20% for training and a different 80% for validation. Now, what happens is we have more stable results because of this. Okay. Why do we have more stable results? Because first, we are not dependent upon one validation set. We have actually 5 different iterations, and for each iteration, we have training, and for each iteration, we have validation. Okay. So whatever validation result we come out will be the average of all of these 5 iterations. Now, generally, an average of 5 iterations will be more stable than just one time. Okay. And this is true because if there are variations, multiple tests will balance out the advantages, or the if some sample has more accuracy or some sample has less accuracy or less precision or less recall and so on. Over the 5 iterations, all of these numbers will get averaged out. They will get a more stable, balanced result. That is one advantage. The second advantage is I get more data. Okay, how do I get more data? Because of 5 different tests, I get 100% for 100% of my data. I am doing validation. Okay, so for this part, fold 1, fold 2, fold 3, fold 4, fold 5, all of these parts of data go into the validation model. So I get a better result. I can know how my model is doing when each of these parts are what do you say, unseen to the model. Okay, so in every iteration, I know that there is some unseen part of the model, and for that unseen part of the model, I get to know how the validation looks like. So I know that I have more data for training. Okay, so here you see in the last case, this 40% of the data, 20% and 20%, we don't get to train the model with. They are only used for testing. But now I get 80% of the model for training, and in fact, I get 100% of the model for training as well, because over 5 iterations, I have seen 100% of the data. Okay, so now we have more data to train. There is only one con for this method, and the con is it is slow. And it makes sense why it is slow, right? We are doing the training 5 different times. For a 5-fold split, we are doing the training 5 different times. So it will take more time. Okay, that is probably the only con with this method. Okay, this is again a commonly used method, cross-validation. Maybe in the learning phase, in the beginning phase, when you are trying to understand the algorithms, that is the only place where you will use 3-way split. But for most of our data, after our project is done, we will use cross-validation for training the model. Okay. Another caveat or another reason for this, or another viewpoint is, again, it depends upon how much data do I have. If I have too much data, okay, let's say I have 10 million points for data and I require only 5 million points for data, then I may go for a 3-way split also. Why? Because for such a huge data set, if I do cross-validation, it will take a very long time for training. And since I have huge data set, my hope is that most of that data set will represent all the different variations that I want to see in the target variable. Okay. In that case, even with more number of data, I can get away, or I can be happy with three-way split validation as well. Okay, so I hope cross validation is clear. Let me go to one more example of, okay, maybe let me finish this diagram and then we'll go. So with cross validation, then what is the strategy? The strategy is this: we will take all of our data and we'll divide it only into 2 parts: training data and test data. You can do any split that you want. If you want 70-30 split, you could do 70-30. I generally prefer an 80% split for training and a 20% split for testing. Okay. Once you have this train and test division, then all of the train data we use with cross validation. Okay. In this case, I'm using a 5-fold split, but again, depending from problem to problem, you may go for a 3-fold split or a 5-fold split or a 10-fold split, depending upon the scenario. In this case, I go for a 5-fold split. And in this 5-fold split, we will use this to find the parameters of the model. So when I say parameters of the model, we'll be learning the different parameters, like the different theta values, different k values, different decision tree structure, and so on. Once we have learned our parameters from this training data, we will test it on the test data, or we'll evaluate it on the test data. So that will be the structure for our cross-validation method. Okay. An extension of the cross-validation method is something called as the stratified cross-validation. Okay. Let me explain to you what this is. Okay. Let's say I have a data set like this, which I divide into 3 folds. Okay. A very good example of this data set is, let's say I have the iris data set. Okay. As you remember, we had seen the iris data set in our matplotlib explanation. And the iris data set is basically a data set of 150 points, which is divided into 3 sets of 50 each. The 3 sets stands for 3 genes of flower: the iris vetosa, the iris versicolor, and the iris vetosa, iris versicolor, iris virginica. Okay. So these are the 3 species of the iris flower. We have 50 data points for each. Now let's say I have these 150 data points and they are sorted. That means the first 50 points are iris vetosa, next 50 points are iris versicolor, next 50 points are iris virginica. In this case, for a sorted data, if I divide into 3 splits, fold 1, fold 2, fold 3, and all of fold 1 belong to the class table 0, all of fold 2 belong to class table 1, and all of fold 3 belong to class table 2, then we have a problem. The problem is this: in the first iteration, we will use class 0 for validation and class 1 and class 2 for training. Now, if you remember, when I talked about machine learning earlier, I talked about that our training environment and our testing environment should be same, okay, or should be similar. That is what we expect. Only then we can expect a machine learning algorithm to work. The prerequisite is your training and your testing environment should be similar. Okay. In this scenario, our training environment has seen only 2 classes, class 1 and class 2. Whereas our validation environment has seen only 1 class, which is class 0, which means that I'm training on 1 and 2 and I'm testing on 0. So this will not work out. The reason it will not work out is my model has never trained from class 0. How can it predict for class 0? Okay, so this is a very bad example of training. Similarly, for the second iteration, I'm training with class 0 and class 2, whereas I'm validating or I'm testing with class 1. Again, a bad strategy, right? So in this case, this method of cross validation will not work out. Okay, the reason it does not work out is we have sorted classes. Okay, we have these 150 points of data. They are sorted in 50-50-50 for vetosa, versicolor, and virginica. So in that cases, what we want to do is we want to go to an advanced strategy called as stratified cross-validation. In stratified cross-validation, we will ensure that all of our validation set and all of our training sets, they have equal distribution of data. Okay. So here, if you look at the second part, uh, here we have multiple splits. We have 6 splits, in fact. Okay, split 1, 2, sorry, multiple folds. Fold 1, 2, 3, 4, 5, 6. Okay, and you can understand how these folds have been made. In fact, we started out with 3 folds: fold 1, fold 2, and fold 3. And each of the folds we have again divided into subparts. Okay, so here this belongs to, all of it belongs to class 0. So we just take one part of it for our validation. One part of class 0 goes for a validation. One part of class 1 goes for a validation. One part of class 2 goes for a validation, which ensures that we have equal number of examples for validation, and all those examples have an equal distribution of data for class 0, class 1, and class 2. Then when I train using this part of the data, I can see that I have representation of class 0, representation of class 1, representation of class 2 for training, and similarly representation of 0, 1, and 2 for testing as well. So this is a good strategy now. That means my training and my testing environment are similar, or the distribution of my data over the target is similar for the training and testing. And this scenario helps us to train our model better. Now, all of these splits, okay, these 3 splits, that is our 3-way split, cross-validation, and stratified cross-validation, we have tools from a package called as scikit-learn, which maybe just after we will explore scikit-learn, and we will see that those tools of scikit-learn, they help us to split up our data in training, validation, and test. So this splitting up we don't have to do manually. Okay, we have tools available that help us to do this strategy. Now I want to move to another concept before we move to our data set. Okay. Let me skip through the slides. Okay. The concept is called fitting. Okay. Now, some of you may have been through some data science course, or you may have some background in data science, or at least some exposure to data science, and you may have heard these 3 terms: underfitting, overfitting, and normal or perfect fitting. Okay, and I'll try to explain in some simple ideas, simple concepts, what do we mean by these things. Okay. Okay. And for this, what I will use is I will use 3 graphs. Okay, let me first draw those, and then we'll see. Okay. Maybe not a very good example. Let me write this. Again, not a good example. Probably. Okay. Let's imagine that this is the data that we have, and on the x-axis, I've got my features x. On the y-axis, I have my target label. And this kind of a problem is a regression problem. Okay, this is not a classification problem. What I mean by a regression problem is if I get this input, I will give out this output. If I get this input, I will give out this output. If I get this input, I will give out this output. Okay, so my output is not a class. Okay, it is not a class like survived or not survived, Versica, Virginica, Versicolor, or Setosa. Oh, Setosa is the third one. Okay, nonetheless, those are not the labels. My target class is not classified. It's not in classes. In fact, my target class is a variable. Now this y can take any values for these x that we provide. Okay, and let's just imagine that this is our data. This is our input, and this is our output. They are represented by these dots. Now, when I try to learn a model out of this, I can have multiple scenarios in what I learn. Okay, so before we edit this, let me make a copy of it. Okay, and I will show you three examples. One is for underfitting, one is for normal fitting, and one is for overfitting. Okay. Let's say in the first case, I say that I fit this data with this model. Okay. In the normal case, I say I fit this data with this model. And in the over case, I say I fit this data with this model. Okay. So let's say these are our three scenarios of underfitting, normal fitting, and overfitting. Okay. And what these three scenarios represent is what is the complexity of the model, or what is the complexity of the equation I'm using to represent this data. Okay. In the case one, in case one here, I will say that I'm just using a line to represent this model. Okay. So when I say I'm using this line to represent this model, my estimate of the line would be something like this. I would say y is equal to a0 plus a1 x1, okay, or a1 x. That is my model. Okay. A0 is probably the intercept that I get here, and A1 is the slope of this line. So if I have the slope of the line and y-intercept, I can draw a line. And this red line, this model, can be represented by this equation. In the normal fitting, I'm going with an order 2 equation. This would look something like this. I say y is equal to A0 plus A1x plus A2x square. And I say that this is the model I'm representing here. Okay, this is a parabolic equation which has a square term in my equation. In model 3, I will have an equation like this. I will say y is equal to a0. So let me just count here. 1, 2, 3, 4. 4 maxima minima, that means an order 5 equation. This would be a0 plus a1x plus a2x square plus a3x cube plus a4x raised to 4. Maybe add one more term for a5x raised to 5. So this equation is represented by an order 5 equation. Okay, so I have different coefficients, different number of coefficients for underfitting, normal fitting, and overfitting. Let me note them down. I have 2 coefficients, 3 coefficients, and 1, 2, 6 coefficients here. Okay. Now, in of these 3 cases, of course, since I've named it this way, the normal case is the best model for these 3 cases. Okay, the normal case is the best model for 3 cases, and the reason is this. Okay, our purpose of training this model, or our purpose of trying to estimate how our model is working, is based on the idea that I want to generalize my answer for unseen scenarios. Okay, when I come across data which is new, I want to know for that new scenario, how will my output work? Okay. If I go with this model, then let's say I have an unseen data somewhere here. For this unseen data, I will be predicting this, which is actually very fine. Let me look at this example. For this data, I'll be predicting something higher. For this data here, I'll be predicting something in this region. And for this data, I'll be predicting something lower here. Okay. So we see for all these 3 scenarios, I have maybe an unseen data here. For that data, I'm predicting this output. So I'm getting one output here. For this scenario, I'm getting an output here. For this scenario, I'm getting an output here. Okay. You can see for the same data point, for the same input in all 3 cases, or similar input in these 3 cases, I have 3 different predictions. Okay. Prediction number 1 is over. So it is predicting something higher than what I would expect looking at this data. This prediction is close to the data that other data points are experimenting. So my model is experiencing something called a saturation. And in the third case, I am under predicting the value. Okay. Now, the effects of this underfitting, normal fitting, and overfitting is more visible when my data that I'm testing with represents how far it is from the actual, or how far is it from its neighbors. Okay, so here, if my neighbors are here, I would expect my answer should be very close to my neighbors. Here, this works well. Here, it does not work well. So both cases, underfitting and overfitting, are actually bad fits of my data, bad fits for my model. The reason for that is this equation, the underfitting equation, is actually a very simplistic model. For this data, my model is very simplistic. That means even if I learn the best values of A0 and A1, this equation cannot represent this model. Okay, the equation is not fit, or the equation is not capable of representing this model. And when I come across this scenario, I call it underfitting. This is also called a scenario with high bias and low variance. Okay, it's also called a model with high bias and low variance. In the third scenario, when I'm having something called as overfitting, in this case, I have a very complex model. Okay, I have a model which is of order 5 for this simple explanation. Okay, for the simple data, or at least simpler in terms of, at least it is not as complicated as a 5-order model. Okay, so for this data, I have a 5-order equation, which says that I have too many variables to learn. Since I have too many variables to learn, I have more flexibility in adjusting how exactly this model will work out. Okay. Since I have the flexibility in adjusting how exactly this model will work out, training this kind of model will do its best such that the training example will give you high accuracy. You will get high accuracy on the training data set. The problem with this is I don't really want very high accuracy on the training data set. What I am more interested in is in the accuracy of the validation set and the accuracy of the test set. And since it is just this model will try to fit the data best for the training set, it will make some wrong decisions regarding such variations. And these variations, they will spoil, or they will do very bad for unseen data. And this very bad for unseen data is a problem. I need a model that represents very well generally how my data would look like. That is, it will do well on the unseen data set. Okay. So here, another reason, or another saying is, we say I have low bias and high variance. Okay, low bias and high variance. And finally, we come to our normal scenario, where we say that this model represents my data best. That means it will give me good results on training dataset, training accuracy. It will give me good results on validation dataset, validation accuracy. Okay. Now the problem is here, if you have the flexibility of plotting this data and plotting the model, then by looking at the plots of the data and plots of the model, you can tell what is the scenario. You can tell, is it underfitting, normal fitting, or overfitting. But in most cases, we cannot plot the data. The reason is our data is high dimensional. There may be more number of features that we have. So till 2, 3, 4 features, we do some visualization to find out how it looks. But after 4, if you have 5, 6, 7, 8, 9, 10 features, or maybe even hundreds of features, it is impossible to visually identify if we are in underfitting, normal fitting, or overfitting. And in those scenarios, when we cannot visually identify, we take help of learning curves. Okay, what are learning curves? Learning curves are graphs that talk about, with number of iterations, or as I increase the complexity of the model, how does my training accuracy or validation, so if I'm talking about accuracy, how does my training accuracy or my validation accuracy change? Okay. And depending upon these learning curves, that is, on the x-axis, I have either the complexity of the model in terms of number of features that we add, or in terms of iterations, how many iterations we train for. If that is on the x-axis, and on the y-axis I have accuracy, then I can see the performance of my model for training, validation, and testing. And what is the best stopping point? This best stopping point is validation when the validation accuracy is maximum. As long as the validation accuracy is increasing, we will try to make our model more complex. But after a certain point, my validation accuracy will start reducing, which is a hint for me that after this point, I am going into the region of overfitting. In the beginning part, I am in the region of underfitting. And this max part, okay, where my data is, where my accuracies for the validation set is the maximum, is the part where I will say I am under this scenario, normal fitting. And I want to stop at this scenario, choose these values, and use those values to train my model. Okay. So this is what we term by fitting. Now, to use fitting or to fine-tune our model, there are several hyperparameters that we can play with. So if you look at the KNN dataset, K nearest neighbors, we know that the number of neighbors is one of the hyperparameters. And as we choose different values of number of neighbors, our accuracy or our score will depend upon that. Now we need to identify what is the best accuracy for the model. Okay, what is the best number of neighbors that we should look at? So we would have to do multiple iterations. Now these things, these knobs or these weights or these values that we change can be divided into two parts: parameters and hyperparameters. So I'm moving quickly towards something called as a concept of fine tuning. Okay, so we have model parameters that act as weights of the model, or for decision tree that would be the structure, the tree structure of the model, and things like that. So these are the model parameters that we are trying to learn from our training data set. Apart from these model parameters, we have something called as hyperparameters. Okay. One second. We have something called as hyperparameters. And hyperparameters are things that will control the training of our model. Okay. So they are not directly parameters, but they affect how these parameters are going to be trained. And there can be many hyperparameters that we have. And since these hyperparameters don't see data, it is generally left to the data scientist to choose what are the hyperparameters you want to use for this model. And without testing your hyperparameters, it becomes a very complex part on the part of a data scientist to choose what hyperparameters will work out best. Okay, so we have to look at methods, at formal methods of identifying what should be the values of these hyperparameters. Before that, let me give you some kind of distinguishing between what are parameters and what are hyperparameters. So parameters are required by the model when predicting. Once you have trained your model, you will be using your parameters to find out your prediction. So just like for naive Bayes, we will learn the parameters, which are the probabilities of different sets and attributes. Those are our parameters, and we need those while predicting for unknown scenarios how the answer will be looking. Okay, and in contrast to that, our hyperparameters are required by the processes to estimate the model parameters. To learn the model parameters, we use hyperparameters. But hyperparameters are not important when predicting the model. Once the training is finished, deploy the model, hyperparameters are useless. We don't need them then. Okay, but we need them for the process of training these parameters. Secondly, the parameters are learned from data. Okay, I use the data to learn which parameters work best and which don't. For hyperparameters, it is generally specified by the practitioner. So the data scientist or data analyst in this case would tell you which hyperparameter will work best. So that is again one difference. Parameters learned from data, hyperparameters specified by the practitioner. Now we will change this part. We will do something more interesting so that even the hyperparameters we can learn from our data, which is a better approach because the practitioner is a human and can make mistakes, right? Data is, you could say data is more unbiased, is not prejudiced. And because of that reason, data can probably give out better results for hyperparameters. Anyways, we'll see this. Parameters are generally not set manually. Okay, if you have to set parameters manually, there is no point of machine learning. The whole part of machine learning is automatically learn the parameters of the model. Whereas hyperparameters are generally set using heuristics. So heuristics are just a fancy way of calling thumb rules or guidelines. Okay, so we use certain guidelines or we use certain thumb rules for predicting what hyperparameters are. That is the general scenario. In our case, we will see that we can move to a little better way of finding out the hyperparameters. The fourth point is parameters are saved as part of the learned model. So this is making just the first point. Since we need the parameters for predicting the model, for predicting for unknown scenarios, we can say that it is once we learn the model, we deploy the model, the parameters go as a package in part of the model. Whereas the hyperparameter, they are just tuned for giving the predictive model problem. Okay, they are tuned for each model. They are not used for predicting. Thereby, they are not learned and they are not saved as part of the learned model. Okay. Now, there can be many hyperparameters that we go across. And since we go across many hyperparameters, we need some kind of a systematic way of seeing which parameter values we choose and how do we choose them. Okay. So here I'm giving you an example of data for house prices prediction. Okay. We have a data for house price prediction. And for this data, we are using an algorithm called as random forest regressor. And for this random forest regressor, we are trying to learn the different parameters, the different hyperparameters, and what should their values be. Now, generally, Python is a very readable language. Okay, so even as you read this model, I have not explained this code to you right now, I am guessing that you can still figure out some of the data or some of the information from this model. So let me ask you a few questions, and so that I want to see if you can read this model, read this code without me explaining the code. You can read this code and find out some interesting information. Okay. So in this code, we are trying to learn certain hyperparameters. Can you name some of the hyperparameters that we are trying to learn from this data? Okay. At least few of these hyperparameters. Can you put it in the chat box? Okay, someone has written param grid, max features, right? Estimators, okay, and estimators, that's right. Okay, great. So, so you're able to read this code. Excellent. So here we are looking at three different hyperparameters that we're trying to learn. We're trying to learn n estimators, max features, and bootstrap. Okay, and in the beginning of the code, we do not know what should be. We do not know what will be the final values that we will get up with. So we try for multiple options. In fact, as the name suggests here, param grid, which is the name of the variable, we are saying that param grid is basically parameter grid or hyperparameter grid. What is the grid in which we are trying to search? Okay, we are saying that for these n estimators, I want to test three different values, 3, 10, and 30. And I want the model to tell me which of these three values is the best value for my scenario. For max features, I want to try 4 options, 2, 4, 6, and 8. For bootstrap, I will try false. So here I'm not trying to learn it actually. I'm just saying in the first scenario, since I'm not specifying bootstrap, what I mean is use a bootstrap of true because that may be the default value. In the second scenario, I'm changing things a little bit. I'm saying choose a bootstrap of false, and for false, test between these two parameters, these two values of hyperparameters for n estimators. 3 and 10. And for max features, use 2, 3 and 4. Okay. Can you tell me what is the type of this variable param grid? What is the data type of this variable param grid? Okay, that's a list. Excellent. So you can see for param grid, I'm providing a list of scenarios. In the first case, I'm using a dictionary with these two elements, n estimators and max features. For n estimators, use 3 values. For max features, use 4 values. Okay, and so on. Can you tell me what? Okay, it's fine. I will answer this. We'll do it a bit faster in that scenario. The algorithm that we're using is random forest regressor. And in this random forest regressor, these are the hyperparameters that we are trying to estimate. Okay. We use a method called as grid search, which comes from scikit-learn. Okay. So from sklearn, which stands for scikit-learn, that is the name of our package. Inside our package scikit-learn, there is a module called as model selection. From scikit-learn's model selection module, we are looking for grid search function. Okay. The grid search, so in fact, a class. This class grid search we will use to search from all of these parameters. So I take my regressor, which is a random forest regressor, create an instance of it called as forest underscore reg for forest underscore regression. Then I create an instance of the grid search model, grid search CV. So grid search CV for cross validation. Grid search CV asks for multiple inputs. The first input is, what is the algorithm that you want to search in? So we say, okay, I want to search for this instance. That is an instance of random forest regressor. The next input is, what are the parameters that you want to search for? So we say, take this parameter grid, which tells you what are the parameters and what are the values that I want to search for. Okay, so it gives here. CV tells us how many cross-validation folds do you want. So we say, go for a 5-fold split. Okay, CV stands for cross-validation. And we are saying we want to split our entire data into 5 parts. So we understand how cross-validation works, right? 5 parts, we will do it in 5 iterations. And for each iteration, we will use one part as validation and the other 4 parts as training. And we'll keep on doing it in, keep on changing the parts for validation in each of the iteration. So that is CV is equal to 5. Then we are asking, how do you want to score? How do you know one setting is better than the other setting? How will you measure it? So we're saying it, measure using this metric, which is negative of mean squared error. Okay, so this is one of the metrics for regression problem. The negative of mean squared error we'll be using as a scoring algorithm. So with these inputs, we set up grid search CV. We create an instance of it in the variable grid search. Now we will train the model. The way we will train the model is we'll look at grid search and we'll say grid search dot fit x, y. Okay, x is our input features, y is our expected output features. So when we do this, it will search through all of these combinations. Okay, can you tell me how many combinations we will have in this entire parameter grid? How many combinations of parameters are we testing? Okay, so someone is telling 3. So let me give you a hint. The hint is it is much greater than 3, 5, and so on. Okay, the number of parameters, the number of scenarios that we're testing is more. Okay, someone has answered 12. Okay, so it is more than 12. 36. 36 is too high. Less than 36, more than 12. Okay. Anyways, let me tell you how we can do it. So we have 2 major scenarios. This is dictionary 1, dictionary 2. For dictionary 1, there are 2 features. N estimators having 3 inputs or 3 different options. Max features having 4 different options. So I will have 3 options and 4 options. So how many scenarios? 3 and 4. It will give me 12 scenarios for first option. Okay. For each value of n estimator, I will go for each value of max features. That means when try n estimators as 3 and max features as 2. So 3, 2 is one set, 3, 4 is one set, 3, 6 is one set, 3, 8 is one set. So like this, for 3, 10, and 30, we will have 12 different options for first case. For second case, this is one option, 2 options, and 3 options. Okay. So the number of scenarios we'll have now is 6 scenarios. 1 into 2 into 3. Okay. This is fixed. 2 into 3 give me 6 scenarios. And the total number of scenarios will be the addition of 12 plus 6, which is 18 scenarios. Okay. So our model will try all these 18 scenarios. And after trying all of this, so see, for each scenario, I have to run the model 5 times, right? Because I have a cross validation of 5. For each scenario, I'll run it 5 times. So that is the number of times our training will execute. Once it executes through all of these 18 different hyperparameters, okay, and for each case, it checks for the validation score. The best answer it returns back. Okay, so here we can see what are the best parameters it has returned. It says that from grid search.best parameters, it has returned a max features of 6 and max or n estimators as 30. So the scenario that works best is this one, 6 and 30. Okay. Out of the 18 scenarios, this one scenario gave us the best results. Okay, so the grid search can help us to fine tune or to find out what are the hyperparameters that works best for our model. Okay. So this is just going ahead. Once we see the best parameters, we can also get from grid search the best estimator, which is a random forest regressor with all of these options set. Okay, we can also see what are the CV results, what are the cross validation results. That is for each of the different options that it tried, which one we got best. Okay, so here we see the different scores of the model. Okay, so this is the sklearn. I am not sure. I think you have to do an install of scikit-learn. As I talked about earlier, it can simply be done by using the command pip install scikit-learn. So I am almost 80% sure you have to write it as sklearn. Otherwise, you just check it out on Google. It may also be scikit-learn. Okay. I am not sure what is the exact phrase you put, but you can check it out in Google. It's not very difficult to do. If you're doing it in a Jupyter notebook, you can start out with putting an exclamation in your cell, saying exclamation, and then pip install sklearn or scikit-learn, and you can install scikit-learn in your system. Okay. So with this, I think we are ready to explore. We are ready to go ahead in a Titanic data set. Okay, we can in the next class for the Titanic data set, we will see. We have prepared our data. We have learned our models. Now we will implement and see how our code performs or how these algorithms perform on the data set, and we can get some scoring out of it. Okay. So see you guys in the next class, which will be on Monday. I may provide some some testing code to ma'am, and she can coordinate with you guys and see how it works out. Okay. So see you guys on Monday. Have a good day. Bye bye. How many classes we have? Let me. I think we'll be finishing on 28th. Either 25th September or 28th September. We have a few more classes left. We have to look at classification examples. Then in the next week we will look at regression and some regression example, and then we'll be done. Okay. Okay then. Thank you so much. See you later. Bye bye.